All right, so this video is going to go into examples. So you're going to find some indefinite integrals, which is the same finding as the antiderivative. Now our answer is going to be of the structure capital F of x plus c, where capital F of x is the antiderivative, and then we're always going to attach this plus c at the end because it's going to be a family of functions in which we get as the result of finding the antiderivative or finding the indefinite integral. So our answer is going to have that structure capital F of x plus c, where capital F of x is going to be the antiderivative. And to do these, I'm going to use the integration formulas that I briefly showed in the previous video. Now I'm going to actually apply them. And these are just some examples I made up. So for example 1, we're going to find the integral of x with respect to x. So the integral of x is what we're trying to find. And one of the rules, so one of the integration rules that I'm going to use for this one is this rule. So I'll go ahead and write it. So we're going to be, anytime you integrate x to the n, that's going to give me 1 over n plus 1, and then x to the n plus 1, and then always attach the c. So the pattern is we add 1 to its exponent, and then you divide by that same value. So for the derivative, it's different. So recall when we took the derivative of x to the n, we dropped down the exponent and then subtracted 1 from it. So it's n times x to the n minus 1. So don't confuse those two. So when we're doing the antiderivative or integrating, we're adding 1 to the exponent, and then you also, whatever that result is, you divide by it too. So for our case, when we're integrating x, you could write x as x to the first power. All right, so our exponent's 1. So this will equal 1 over 1 plus 1, and then x raised to the 1 plus 1, and then plus c. So that's 1/2 x squared plus c. All right, that's our answer for that first example. So our capital F of x is the 1/2 x squared. All right, so that's it for that one. Now number 2. So we have an integral, and notice this, it's blank, it's just dx. And this is the same thing, as it might be helpful to just go ahead and write it as 1 times dx, since 1 times anything gives you that same quantity. And why that's useful is because I'm going to use the rule anytime you integrate a constant where it's k dx, that's going to give me kx plus c. All right, that's why I wrote it like that. In this case, k is 1. So that's going to be 1 times x plus c, so just x plus c. All right, so just anytime you have the integral where it's just sort of like a blank integral, you just have dx, it's always going to result in the x plus c, because it's really like 1 times dx, where 1 is our value k, in which we're using that rule. Integrating k, you get kx plus c. In this case, it was 1 times x plus c. So for the third example, just like how you can factor out a constant in front of the derivative, you could do the same thing for an integral. So what I'm going to do is bring the 3 in front of the integral. So factor the 3 in front of the integral, and then focus on integrating x. All right, now we know for x, it's going to be 3 times, and we use that rule where we add 1 to the exponent and divide by that value. So again, the rule, if you integrate x to the n, 1 over n plus 1, and then x to the n plus 1 plus c. And in this case, we have the derivative of or the integral of x, and that's x to the first power, so that's going to be 1 over 1 plus 1, and then x to the 1 plus 1. And then we have the constant that we attach. So that's 3 halves x squared plus c. All right, and the general gist of that is that you just factor out the constant in front of the integral, and integrate whatever the function is involving x. So I did the first example was x dx. I gave 1/2 x squared. Here we're doing 3 times 1/2 x squared. All right, so those are those 3 examples. Now here are some examples from the textbook. So example 3, page 251, it's got 3 parts, A, B, and C. All right, so I'm integrating 1 over x cubed. Now I want to use the rule because I have this something of the structure, so I want to use the rule. We have x to the n and dx. All right, that's the rule I want to use. But because the x is in the denominator, I need to do some rewriting. So I would rewrite this. So I'm going to rewrite first. Well, anytime I have 1 over x cubed, I could write that as x to the negative 3rd power dx, just by rules of exponents. Now I have it of this structure. So now I'm going to apply the rule. So it's going to be 1 over, and I add 1 to negative 3 plus 1. And then x to the negative 3 plus 1, and then plus c. So what is that going to give? So that's negative 3 plus 1 is negative 2. So this will be equal to 1 over negative 2. And then x, negative 3 plus 1, x to the negative 2 plus c. And then usually we don't want our answer to have negative exponents, so I'd bring the x into the denominator. That's going to give 1 over negative 2x squared plus c. All right, so the rule, I guess not the rule, but the idea is to rewrite it first and then apply one of the known integration rules. So part B, the square root of x dx. So again, I'm going to use the same rule, but I need to rewrite it into a format which I can apply the rule. So the square root, anytime you have a square root, that's the same thing as raising it to the 1/2 power. So this would be like x to the 1/2 dx. So now I apply the rule. So that's going to be 1 over 1/2 plus 1, and then x to the 1/2 plus 1, and plus c. And 1/2 plus 1, that's 3 halves. And then x to the 3 halves plus c. But I'm doing 1 divided by 3 halves. That's the same thing as the reciprocal of 3 halves. The reciprocal of 3 halves is 2/3. Right, so it's 2/3 x to the 3 halves and then plus c. So you could know that if I have a fraction for the exponent and you add 1, it results in a fraction. Whatever the result is, you take the reciprocal of it. So for this case, the 1/2 plus 1 is 3 halves. So then I take the reciprocal, that's 2/3. That's what goes in front of the variable. All right, so that's that one. The next one. And the next one is involving a trig function. So you're doing 2 sine, and then it should be sine x dx. Okay, so like derivatives, you can factor out the constant in front. So for integration, I'm going to factor out the 2 in front and then focus on integrating sine. And that's where I reference my list of rules. And integrating sine is this one. So we get negative cosine when you integrate sine. So that's going to be 2 times negative cosine x plus c. Or just negative 2 cosine x plus c. All right, so that's that example. Now the next example is on page 252, and it's example 5. All right, so we're integrating, and it's x plus 1 over square root of x, and then dx, all right? So I want to be able to use the rules that we know. And what I'm going to do is try rewriting first. Into a format in which we can apply the new integration rules. So it's just going to be doing some algebra manipulation. So for one thing, the square root of x, I could write that as x to the 1/2 in the denominator. So I have x plus 1, x to the 1/2 dx. So I can, by rule of fractions, I can separate this. So I have x over x to the 1/2, then plus 1 over x to the 1/2. So I just broke it up into 2 fractions just based on adding and subtracting fractions. And the 2 fractions have the same denominators, x to the 1/2. Then I can use like exponent rules. So for x over x to the 1/2, you do x to the first minus 1/2 just by division with exponents. So it would be x to the 1 minus 1/2. And then plus, and then 1 over x to the 1/2. If I'm going to write that into a format which I can apply the rules, I could write that as x to the negative 1/2. All right, so 1 minus 1/2, that's x to the 1/2. And then plus x negative 1/2, and then dx. Now I can apply the rule that we've been using. Right, so I can apply this rule. Now you could, if I want to get real technical about it, you could write this as integrating each piece, integrating the x to the 1/2 dx piece, and then plus integrating the x to the negative 1/2. All right, so you're just integrating each piece. Okay, so now I apply this rule to each piece. So the first piece, I'm going to get 1 over 1/2 plus 1, and then x to the 1/2 plus 1. And then I'll worry about putting a plus c at the end. Then for the other one, you get 1 over negative 1/2 plus 1. And then x to the negative 1/2 plus 1. And then I'll put the plus c. All right, so 1/2 plus 1, that's 3/2. So I have 1 divided by 3/2, and then x to the 3/2, which we know we take the reciprocal, it becomes 2/3. Negative 1/2 plus 1, so that's 1/2, so this will be 1 over 1/2. And then x to the 1/2, and then plus c. So take the reciprocals, so that becomes 2/3. X to the 3/2, the reciprocal of 1/2 is 2, so it'll be plus 2. And then x to the 1/2, and then plus c. And I'm fine with this as like an answer. The textbook just goes further with the simplifying. And by how they simplified it, well, for one thing, we have 2 out of the 2/3, and we have 2 in the other value. They factored out a 2, and they also factored out so the x to the 1/2 has the smallest exponent, so you could factor out an x to the 1/2. And what does that give me? So you take away 2 from 2/3, that's going to be 1/3. And then x, and you take away 1/2 from 3/2, so you do 3/2 minus 1/2. That's going to give, so this would be like scratch work off to the side. So you did x to the 3/2, and then you subtract out 1/2. That's x to the 2 over 2, which is just x. So it's 1/3 x, and then plus x, or plus 1, and plus c, because you're taking away the whole thing, 2x to the 1/2. Which you could write this as 2 square root of x, because that's what x to the 1/2 is, and then 1/3, and then x plus 1, and then plus c. That's just another format for the answer. So I'm fine with that. The textbook also factors out 1/3, and the textbook answer, very similar to this one, it's just 2/3 square root of x, and then they have x plus 3 and then plus c. That's the textbook answer. So they went ahead and factored out 2/3 instead of factoring out 2. It's just a preference thing. And because you notice if it's very similar to this one, it's just instead of a third, right, that's technically 1x. And then instead of 1, they have 3, because 1 divided by a third is 3. All right, so that's where I'll stop it for this video. In the next video, I'll go into more examples, but real quick, for this one, I rewrote it into a format which I can apply the integration formulas, and I broke it up into 2 fractions using just rules of fractions, and then I just went about simplifying it more so that you get x to the 1/2 plus x to the negative 1/2, and then you integrate each piece, and I applied this rule to each piece, and then just after you do that, you simplify that more. And I was fine with the 2/3 x to the 3/2 and then plus 2x to the 1/2. You can just go further with the simplifying. All right, so that's where I'll stop this video.